We're going to get started. Welcome to the end of year review. My name is Dan. I'm your illustrious TA. Glad to see you all here. I'm going to be writing mainly on this section of the whiteboard, so probably end up somewhere where you can see this just for the sake of the recording that I'm doing for everyone. I'm going to try to mainly write on here. The final is pretty much just the material from the midterm on. Anything that's cumulative is just something, that's naturally cumulative, like having to find an expected value of something. But it will be pretty much in the context that you've been seeing more recently rather than digging back to the beginning of this semester for questions. We're mainly going to be going over exam W19 from the Learning Suite tab. Before we do that though, I'm going to go over just a couple of things briefly. Most of this test is hypothesis tests and regression. Those are pretty much the two things that we've done since the midterm. We've done just a bunch of different types of hypothesis tests, / confidence intervals. We can roll into that too. And then regression at the end. So a couple things to note with hypothesis tests. / a distinction between a hypothesis test and a confidence interval. A confidence interval is not a hypothesis test, and a hypothesis test is not a confidence interval. They're two distinct ideas that just use similar kind of ingredients, So a confidence interval, when we're trying to find a confidence interval, all we're trying to do is we're saying, hey, here's our best guess for some population parameter, right? So if we're finding the confidence interval of the mean, I'm saying, and let's say this is a 95% confidence interval, all I'm saying is, hey, I'm 95% sure that the actual mean lies between two values. That's all we're saying with the confidence interval, and that's pretty much the extent of analysis that we can do with a confidence interval. Is just, hey, we're 95% sure it lies between these two values. Yeah?
If you do like a hypothesis test at 95%, are those values going to be the same as the critical values?
No. Which is an important question. That's a good question because it highlights, I think, some confusion that can come up between hypothesis tests and confidence intervals. Because we're using oftentimes z-scores in both of them, and we're looking at oftentimes a number like 95%, it can become easy to kind of conflate the bounds of the confidence interval with the critical values, but they're different ideas. Once we transition to a hypothesis test, we're now looking at a normal distribution centered around 0, and we're asking how many standard deviations away from the middle is my observed mean, right? My observed sample mean. And then we're essentially finding the likelihood of observing that sample mean given some population standard, right? And so with a hypothesis test, we can then do analysis of, hey, I think that it's unlikely that this is the actual population mean, right? But you wouldn't say a statement like that with a confidence interval. A confidence interval does not give you statistical power to say anything about, about a hypothesis. All a confidence interval gives you is, hey, we're pretty sure that this parameter lies between these two values. I'm going to fill this in with just A and B. Pretty sure mu is between A and B. That's all we can really say with a confidence interval. Okay, any questions on the difference between a confidence interval and a hypothesis test? We're going to talk slightly more about hypothesis tests, but yes, Everett.
Did you say the critical value is how many standard deviations away it is?
So the critical value, our critical value is associated with the level of significance of our test, right?
Whereas the test statistic is the standard deviations away, or?
Well, so they both kind of are.
Okay.
So the test statistic is how many standard deviations away from the center our observed sample mean is, versus the critical value is how many standard deviations away from the mean do I have to get in order to get within the level of significance, if that makes sense. So if our level of significance, say we're doing a one-sided test and our alpha is 0.05, then I would find the critical value, the number on the Z table or T table, associated with where 0.05, 5% of the distribution lies above that critical value, right? So this is the number of standard deviations. The critical value is the number of standard deviations away from the mean such that 5% of all possible outcomes lie above that line, right? So they're both measures. Any score that we're getting from the Z table or T table is standardized in terms of standard deviations, right? So they're both going to be a number of standard deviations, but our test statistic is associated with our sample mean, and our critical value is associated with our level of significance. Does that make sense? Sweet.
Yeah, for the test statistic, aren't you gonna like use that for critical value? You'll set up like your x bar minus mu over variance over n is equal to some critical value, right? Am I doing that right?
So that's going to be equal to your test statistic, that formula that you just said, and then
Right.
you're going to compare that test statistic
To the
to a
critical
critical
value.
value.
Yeah,
You're not going to set them equal, but you are going to compare the two.
So, it's going to see if it's greater or more extreme, and if it's more extreme.
Exactly.
Okay.
If your test statistic is more extreme than the critical value,
Reject
then
that.
you reject the null.
Sweet.
Correct. Where did I put the erasers? If the test statistic is more extreme than the critical value, then you reject the null hypothesis.
Hey, Dan,
Yeah.
is that alpha, is that like that region, is that the rejection region?
Yes.
Okay.
That is
so
also the
everything
rejection.
covered by that 0.05.
Yeah.
rejection.
And we're gonna talk about this slightly more right now. So when you're doing a hypothesis test, there are kind of two rejection conditions that are both sufficient, meaning if either of them are true, then you reject. And the reason why they're sufficient is because they're essentially saying the exact same thing, just like in slightly different ways. So we've talked about how if, let's say this is your critical value, which is associated with this alpha level of 0.05, if you find a test statistic that's more extreme, then we reject the null hypothesis, right? So we can compare critical values to test statistics. And if your test statistic is more extreme, we reject. The other thing we can compare is your p-value to your alpha level. So there's going to be some p-value associated with your test statistic, and all the p-value is the portion of the distribution that lies outside of your test statistic. So right here we're doing a one-sided test, and so my p-value is everything that lies above my line. If we were doing a two-sided test, and I had a test statistic down here too, my p-value would be these two parts of the distribution added up. And then we're comparing that to the p-value, or to the alpha. If our p-value is smaller than the alpha, then we also reject. But kind of intuitively, both of these conditions are testing the exact same thing. It's just asking, are we further outside of the distribution than whatever our critical value is? Because your p-value is going to be smaller than your alpha if your test statistic is more extreme, right? So they're saying the exact same thing, right? They're just two different measures of saying that thing. We talked about various types of hypothesis tests.
Wait, Dan,
Yes.
just to review. So the confidence interval is not the same as the critical value.
No.
Like at all.
No.
Okay. Okay, that's all.
Yep. Cool. Yes.
Sorry, these are probably dumb questions, but would the critical value then be the bounds of the confidence interval on the null hypothesis?
No. Also not. So we don't really have a confidence interval with a null hypothesis, because with our null hypothesis, we're just assuming that there is some value for mu, right? We're saying, okay, I believe that the true population mean is 20. Therefore, there is no confidence interval because I'm just assuming that it's 20, right? Versus if I don't know what the true population mean is, then I would have a confidence interval of, I'm 95% sure it falls within this range, right? Yeah, Chayton.
Are critical values and test statistics always on the standard normal? Because I know you can calculate from just normal to standard normal. Can you have those on the other one or no?
Yeah, so you can have, we've talked about some other distributions, most notably the chi-squared distribution, right? That's not a normal distribution. Or the t distribution is also not a normal distribution. But you can have critical values and test statistics for both of those different types of distributions, right?
Okay.
If that makes sense. So, speaking of that, we've talked about a couple different hypothesis tests. Kind of our classic, our base model for a hypothesis test is if we're just trying to find, if we're running a hypothesis test on the mean of a population, we use a formula like this, where X bar is our sample mean, mu is the true mean, sigma squared is the population variance, and then n is your sample size, right? Now, every other, pretty much, well, I'm not gonna say every other, but pretty much every other hypothesis test that we've talked about is just some riff on this formula, right? So this is gonna give you a z-score, which you use on the normal distribution. And you use this formula if you know what your population standard deviation is, right? And if you're trying to find the mean. Now, if you don't know what sigma squared is, you don't know what the population standard deviation is, but you have your sample, you can calculate a standard deviation of your sample, and we can instead run a very similar test, but we substitute sigma squared for s squared, which is the sample standard deviation. And this is going to give you a t-statistic. Well, not a t-statistic, a t-score. Yeah. Gets confusing with test statistic and t-scores. Yeah.
Say you were to have your sample set and data points for each sample set, or observations for each point, would you calculate your sample standard deviation by using the adjusted?
Yes.
So you would do like 1 over n minus 1 times the summation of all xi minus xr.
Yeah. Yep. And we're actually going to see an example of that on the practice exam that we're going to go over. Yeah, Lindsay.
One more really quick question. Say your population is normally distributed, and it clarifies, like in the problem, that it's normally distributed, but then for your sample, you have something that is like considered a small sample, and you don't know the population standard deviation. In that case, would you use a t-distribution, or would you use, like if it clarifies that the population is normally distributed?
This is a good question. And I would heavily recommend, for anybody who doesn't know yet, there's a flow chart on Learning Suite. Under the Content tab, there's a tab called Distribution Help Sheet. And under there, there's a flow chart that tells you when to use each of the different tests. And so if you know that the population is normally distributed, then you can use a z-score.
Even if
Well,
it's a
actually, you can use a z-score if you know that it's normally distributed and if the sample size is over 30.
small- okay. So if it's under 30, you have to use a t-score.
Have to use a t-score. Yep. So I would heavily recommend reviewing that flow chart. We're going to talk about it a little bit, but I would pretty much memorize that thing. So then, kind of the next one that I want to talk about that looks very similar to these is doing tests with proportions. So with a proportion, I'm not going to use cursive. If you have a binary variable as your variable of interest, you're going to end up with a proportion. And
Wait, Dan, I thought this is Bernoulli. This is just Bernoulli distribution, right?
this is Bernoulli.
Okay.
This is Bernoulli. This looks ever so slightly different in that we have p times 1 minus p in the denominator instead of sigma squared or s squared, but it's essentially the exact same thing because p times 1 minus p is just the variance, right, of the population. This is the variance of a Bernoulli distribution. And so we're really doing the exact same thing, right? We're just calculating the variance a different way than in the two previous examples. And this is also going to give you a z-score. It's important to note two things. First of all, I used p in the denominator instead of p hat. The reason why I did this is because the idea whenever we're running a hypothesis is we're saying, well, a hypothesis test is we're saying, okay, I went out and I got this sample of 100 people and I found some mean. I now want to test to see if this mean is statistically different from my preconceived notion of what I thought the mean should be, right? Yeah.
So I think on like this exam actually in 4B, it goes over one where you use p hat in the denominator.
Yeah.
Like why? Like are we gonna get to that?
Yeah. So I'm actually touching on that right now.
I'll leave it up.
No, you're like right on top of it. So we use, well, so we're living in this world. Whenever we're running a hypothesis, we're living in a world where we assume that our null hypothesis is the true value, right? And so if I have a p hat and I'm trying to test it against some p, if I'm trying to make this live in the world where p is the actual population, parameter, then I'm going to assume that p is true every time I plug it into my equation, right? It wouldn't make sense for me to be testing p hat against p and then plug in p hat down here, because that would be kind of contradicting my assumption that p is the true population parameter, right? And so if you're running a hypothesis test and you have an assumed value for p or one of these other statistics or numbers where it's relevant, then you plug in your assumed value, right? It just doesn't come up in these two previous tests because mu doesn't show up anywhere else other than where it is, right? We had a good question though. There is an instance with proportions where we do have to use p hat in the denominator. And that's if we're doing differences in proportions. I'm gonna erase this real quick. If we're doing a difference in proportions, then our null hypothesis looks something like p1 minus p2 equals 0, right? And then our alternative hypothesis would be something like p1 minus p2 does not equal 0. So now, if I'm setting up my hypothesis test, I would say p hat 1 minus p hat 2 minus 0, because that's, well, I'll write it out more explicitly. Minus p hat 1, or p1 minus p2. And then I write this over p1 times 1 minus p1 over n1 plus p2, 1 minus p2, and 2. So this is going to become 0 because our null hypothesis is that they're the same, right? But now we run into a problem down here. I just told you that whenever we have an assumed value for our proportion, we should plug it into the denominator. But we really don't have an assumed value for p1 or p2, right? We've just assumed that p1 minus p2 is 0. But p1 and p2 could be anything as long as they're the same. They could both be 50%, they could both be 75%, they could both be 25%. I can't say anything about what p1 or p2 individually is. I can just say, based off my null hypothesis, that they're the same, right? And so then we have to fall back to, okay, what's the best next, the next best thing than plugging in our assumed true value? Well, then we just have to plug in what we have, which is our p hats, right? So does that make sense? Because we don't really have an assumed value for p1 and p2 in this case, we can't plug them in.
So you only do that when you're comparing.
Only when you're doing differences in proportions.
And then does that give you a Z-score?
This will give you a Z-score. Yeah. Clark?
I was just gonna add, I think, when you're doing, or I wanna ask, when you're doing just a confidence interval for proportion, wouldn't you just use p-hat as well, because you're not comparing it against like a.
Correct.
Okay.
So this is another good comparison of confidence intervals to hypothesis tests, right? If you're doing a confidence interval, you don't have an assumed value for P1, right? Our confidence interval is us trying to say, okay, we think that P lies within two values, right? So because we don't have an assumed value for P in a confidence interval, we also use P hat. Good point, Clark.
And that would just be set up as P and then over in the denominator would be P hat, 1 minus P hat. How would you set up if you're doing the confidence?
So if you're doing a confidence interval with proportions, we would do P hat plus or minus whatever our test statistic is, square root of P hat 1 minus P over N.
And by test statistic,
That will be your Z
That's the
score.
Z-score.
If you're doing like a 95% confidence interval, this will be 1.96.
okay, so we can I just put Z score instead?
Sure, yeah.
Because that kind of threw me off. My fault.
No, you're good. One other note, really quickly on proportions. So Bernoulli is a different distribution than a normal distribution, right? Like you're either a 1 or you're a 0 if you're answering Bernoulli. So this causes some complications when we run our hypothesis tests because we're turning it into a normalized value, right? We're turning this into a Z-score, which is on the normal table, but Bernoulli is not normal. So we have to invoke the central limit theorem when we're doing proportions, and we can only run a hypothesis test on proportions if our sample size is large enough, if it's greater than 30. If it's less than 30, then we know that the underlying distribution is not normal, and we have too small of a sample size to use the central limit theorem, so then we can't get a normalized test statistic to compare it against. So if sample size for proportions is less than 30, can't do the test. Cheat.
Is there an exception if they give you what it is?
We're going to talk about this one in just a second. We'll talk that one through a bit. We didn't do P-pooled at any point this semester, right?
No.
I think we axed that. Okay, that's too bad. P-pooled was kind of fun. All right. And then the only distribution I haven't written up here is for chi-squared. The chi-squared hypothesis test, which is pretty simple. When do we use chi-squared? What makes it different from the rest of these? We're looking for population variance instead of a mean, right? What's even the formula again? Is it S squared 1 minus R? What is it? Who? Somebody read it off for me.
S squared n minus 1 over 6.
Okay, yeah. Sweet. So this gives you a chi-squared value. Chi-squared is a little goofy, not only because it looks kind of goofy and is different from the normal, but chi-squared, like on your table as you're reading off the table values, it shades in this area above and gives you, all the area that lies above this point. Whereas on your like normal table, it gives you everything up to some point, right? So you kind of have to read it backwards a little bit in terms of finding p-values and such. But the analysis is still the same on a chi-squared test. You're looking for, is my test statistic more extreme than the critical value, right? All right. That's all I had for talking about different hypothesis tests, but
You can still do two-tailed tests on the chi-squared?
you can. It's somewhat more rare. You probably wouldn't see it, but you can. Yeah.
Can you not do like a hypothesis test for a difference in variances?
You can. We just have not talked about that,
So
so you don't need to worry about it. Okay,
I said, can you do
let's start rolling through the practice test then. So the first one Chaitin was just referring to, these are the true-false ones. It says, you select a random sample of 20 Utahns to collect data on whether or not they are employed. If P hat denotes the proportion of people in the sample who are employed, and P is the proportion of people in the whole population who are employed, then that equation is approximately T distributed with 19 degrees of freedom. What think we? I'm hearing false. And false is correct. Just like we were just talking about, we can't say anything about the underlying distribution here because we have too few people. And so it's not normally distributed. It's not a T distribution. It's a Bernoulli distribution, and therefore we can't run a t-test on it.
If it's more than 30, can you do a t-test?
Yes.
Well, no, if it's more than 30,
Well,
it'd be normal.
Yeah, then it's Z. Then it's Z. Okay. B, a consistent estimator is unbiased and efficient. What's the definition of consistent?
It's the same spot a lot.
It's the same spot a lot? That's actually probably closer to efficient, which is confusing because if I try to describe efficiency, I want to use the word consistent because of that reason. You hit the same spot a lot.
This one where it's like, is n approaches infinity, bias approaches 0?
Yeah. So, consistent. With an E? With an A?
E,
okay. Spelling is not my forte. So, something is consistent if bias, I'm going to say X is consistent. If bias goes to 0 and variance goes to 0 as n goes to infinity.
If only one of those is true, then it's not consistent.
Yep, that's true. If either of these fail, then it's not consistent. So what do we think on B? We think false. Why is it false? Jayden thinks it's true. Jamie, what do you think?
Didn't we do like, we did two tests, like if X bar as an estimator and Xi as an estimator, and Xi was, it was biased, but it was still consistent.
Yeah.
So it was biased, but it still had n in the denominator, so it made it consistent.
So that's a good point. That's one potential counter, is to say it doesn't need to be biased to be consistent. As long as n, as Jamie said, is in the denominator, as n gets bigger, the bias is going to get smaller and smaller and smaller, and you can very much have a biased estimator that is consistent.
I was just going to say, does this have to do with the fact that efficiency, you can't say something is efficient, it has to be like more efficient than? Like,
Yeah. So that's the other thing that you could say for this, which, I mean, you don't need to say anything for this, you just put true false. But that's the other thing that's wrong with this statement, is something can't just be efficient. It is a comparative measure, consistency is. And so because of that, a consistent estimator isn't efficient per se. It can just be comparatively consistent or comparatively efficient. So yeah, those are the two issues with this statement. Any questions on that? Yeah.
Can you re-explain consistency and efficiency again?
Yeah. So efficiency, I mean, the classic example that Dr. Leslie gives is with target practice, right? With shooting a bow and arrow. Efficiency is your ability to clump the arrows up on some part of the target. Bias is your ability to hit the center of the target, right? Efficiency, consistency says that as you shoot more arrows, your arrows both get closer together and they also move towards the center of the target, right? That's what consistency is. And so you could imagine, let's think about a couple different kind of estimators. So let's say that our true mean is right here. And let's say that we have one estimator that gives us something that looks like this. And we have another estimator that gives us something that looks like that. So we'll call this one x1 and this one x2. So x1 is clearly biased, right? Because the center of x1 is all the way over here, which is not even close to our value. But x1 is more efficient than x2 because x1 is more clumped up, right? x2 is more drawn out. And so x2 is unbiased because it lands on mu, but it's less efficient than x1 because it's not as clumped up. Now let's imagine that this was with sample sizes of 30, but let's say that if we up our sample size to 3,000, we have our true mean. Let's say x1 becomes this, and x2 stays the exact same. So x1 is consistent because as our sample size got bigger, it got closer to the true mean and its variance became smaller, right? x2 is not consistent because as n got bigger, it stayed the exact same. Yeah.
What would a case look like then when it's consistent but not, or like when it's unbiased and efficient but not consistent?
Well, so the problem with that statement is that efficiency, like x1 in this case, is efficient relative to x2.
Okay.
But x1 isn't in and of itself efficient.
So you have to compare it.
You have to compare
What's
it.
more efficient? Okay.
Yeah. And so, like, there is no such thing as an estimator that is both unbiased and efficient just by itself, because you have to compare it to something else in order to say something about its efficiency.
So something is more efficient and has a smaller variance.
Yep. Yep. Feeling good? Okay. Let's talk about C. When you perform a hypothesis test, the larger alpha is, the easier it is to reject the null hypothesis.
It is easier to reject the null hypothesis.
Look at that. Siri coming in clutch. This is why they don't allow smartwatches in the testing center. Yeah, so as alpha gets bigger, it is easier to reject the null. That's because all we're doing with alpha is we're just setting some arbitrary level, some arbitrary, point in the normal distribution, above which or below which we're willing to reject the null hypothesis. And so if you increase your alpha to a bigger number, then you're just saying, okay, if our alpha originally is 0.05 out here, and then I say, actually, I'm okay with an alpha of 0.1, then we can see visually that it's a little bit easier for our test statistic to fall outside of this range than fall outside of that range, right? So it does strictly increase the likelihood that we reject the null. D, I think, is a question that we no longer cover.
Good.
E is also not something that we cover. We don't cover 2 anymore. Okay.
Whenever we we how do people survive this class in the past? With like just so much more concepts. Like what?
We're gonna be done with the true false for now. And we're gonna do some more hypothesis test practicing. Real quickly, what's the central limit theorem? It's unrelated to this question, but just in general, who knows what the central limit theorem is? Yeah.
You still have to do like n is equal to 30. If n is greater than 30, all like the sides are also going to come together. Also kind of the same idea of the law of numbers.
So they are different. Yeah.
Is the sample size large enough and independent, like the variables are random, then the distribution will follow the normal distribution?
Yeah. Kind of along that line. Yep.
I was just going to say, as n approaches infinity,
That's the law of large numbers, I think. So, admittedly, I don't remember the difference between the two. So, which is why I thought to ask the question, because there's a fairly high chance of like it coming up in some true false or some part of some long answer. So the central limit theorem states that given a sufficiently large sample size, the distribution of the sample mean will approximate a normal distribution. So what that means is not that your sample becomes normally distributed, but it means that if you take a bunch of different samples, the results of those samples will be normally distributed, right? And so slightly different idea there. And then the law of large numbers, which I'm sure Bing will give me an excellent answer for. Let's see. Yeah, is what you were mentioning there at the end. The average of results obtained from a large number of independent random samples converges to the true value. So, central limit theorem says that as we increase our sample size, the distribution of our sample means becomes normal. Law of large numbers says that as we increase our sample size, our prediction becomes closer to the true mean, right? Yeah.
So is it by like invoking central limit theorem that we're able to get a normal distribution on like with binary variables?
Yes.
Because you're looking at the results of the samples, and those can be distributed normally if you have a big enough sample. But yeah.
Exactly.
Okay, but it's not with the law of large numbers because we're not saying that.
Correct. So the law of large numbers, let's say we were taking a sample of people, asking them if they were married or not, then our underlying distribution of our sample will never be normal, right? Because we're going to have a bunch of people that say, no, I am not married, and a bunch of people that say, yes, I am married. This is not a normal distribution, right? And it never will be a normal distribution. If we ask more and more people, it's not going to suddenly turn into a bell shape. It's just going to be that, right? But central limit theorem says, well, if we take a bunch of samples like this, if I take the average of this, well, that looks like it's about 50%. And then let's say I take another sample that looks more like this. That looks more like 75%. And as I plot them all out, then we get a normal distribution, right? Law of large numbers in that same context is saying, well, if I sample 10 people and get their responses of whether they're married or not, I might draw a really wild sample, right? I might find that 90% of people are married. And it probably wouldn't be a great thing to then extrapolate that out and say, okay, 90% of the populace is married. But as I increase that sample size from 10 to 100 to 1,000 to 1,000,000, my proportion is going to get closer and closer to the true population proportion, right? So central limit theorem has to do with the shape of our distribution. Law of large numbers has to do with the value or like the accuracy of our sample means, right? Or our sample parameters. All right, now let's do this hypothesis test example. I'm gonna let you guys get a head start, and then I'm gonna start writing up work on the board. And if you need me to scroll down at any point, just tell me.
Can you zoom in a little bit?
Yes.
Is that good? alpha?
So nice. Also, did you mean to put 35? Up for the end too?
That's what it was in here, but that could not match with.
Oh,
No,
no, you're right,
it
you're
is
right,
good.
you're right, sorry.
All right, I'm going to start going over part A. So, we have a null hypothesis that the means are the same, and an alternative hypothesis that the difference between the two is less than 0. What does this alternative hypothesis say about the test that we're going to run? Yeah.
You're gonna get a p-value that's smaller than your alpha of any value. It's you gotta do to the 10%, 5%, or 1%.
Right. So we're running a one-tailed test, and we're doing it specifically on the low end of the distribution. Right. All right. So this is a difference in means question, and so we use our difference in means hypothesis test equation, which is where we plug in our x bars on the top and we subtract them from one another. We subtract from that our assumed difference in the population means, which in this case is 0. And then in the denominator, we plug in the sample variance of the first over the sample size of the first, plus the sample variance of the second over the sample size of the second, and we add those together. And I say here that we're going to get a z-score. Why is this a z-score, not a t?
Above 30 or 30 and above.
Right. Both of our samples have 30 people in them or above, and so we say by the central limit theorem that it's normal. So we're going to use normal instead of t. And what number do I get here?
Negative.
Yeah.
Oh, well, I got negative 1.0245. But if one of them was a small sample, would it then be t distribution? Or do they both have to be large samples?
You would probably use the t statistic. You'd probably use a t distribution in that case. I doubt you would ever be given a question like that because it is kind of ambiguous.
Yeah.
But yeah. Okay. So do I accept or reject the null hypothesis here? Fail to reject. Correct. I don't accept it. You never accept the null hypothesis. So we failed to reject it. There's no alpha level given here, but this value is never gonna cut it. The p-value associated with this is like 0.15. Typically the largest alpha level that's acceptable is 0.1. So this is gonna fail to land in in our rejection region, kind of no matter what alpha we choose.
Dan, on that, so you can just say that you failed to reject because of the point, right? You just know that off the top of your head, it's not. Okay.
Yeah, and I mean the critical value associated with 0.1, I think is like 1.68, right? And so if you see any number that doesn't, isn't even close to that, then you know that you're going to fail to reject, right? Like a test statistic of this size is, whether it's positive or negative, is never going to be enough to reject. All right.
So the test statistic is the z-score.
Yes.
Okay.
Yeah. So this is gonna, one of these formulas, well, whatever formula you use is gonna give you a test statistic. In this case, it's a z-score because we're dealing with means and we had a sample size that was large enough. All right, let's go on to part B, which is basically the exact same thing, just with larger sample sizes.
Dan,
Yeah.
I have a question on part B though.
Yeah.
Can you just say by the law of large numbers that as you increase your sample size, it's going to get closer to the true? Like, would you have to do the math for this? Like, is my question? I guess you would to prove, because what if the original sample actually did have the correct mean and variance?
Yeah.
Okay.
And as you're gonna see, as your sample size gets larger, your statistical power increases. And so your test statistic is going to change pretty dramatically if you change the sample size.
Right. Well, like, so obviously intuitively, would your hypothesis test from part B have a different conclusion if you increase? I would say yeah, because the law of large numbers of the large law numbers. The law of large numbers would say that it's going to more accurately reflect.
Yeah.
But you would want us to show the math on this?
Yeah, for sure. All right. What do we think on B? What's the answer? Well, what's the test statistic first? Just going to round that to negative 2.59. So our test statistic has become much more extreme by increasing our sample size, right? The only thing that we changed was we erased the 35 and the 30 in our sample sizes in, part of the equation, and we replaced them with 200s. Do we reject or fail to reject now?
You would reject.
We do reject. So the p-value associated with this is like 0.0049. So this is now smaller than all traditional levels of significance, right? So no matter what, we would end up rejecting this. As a general bellwether, I'm pretty sure the critical value associated with 99% is around 2.15. So if you have a number greater than that, you're gonna reject.
Absolute value.
Absolute value. Yeah, absolute value then.
This was a one-sided test.
Yep.
If it were a two-sided test, I don't think it could be with this, but if it were, how would that change anything that we've done?
It would change a little bit of what we've done. It would change kind of. Because it didn't give you a specific alpha level, right? If it had given you, say, for this whole problem, test with a 0.05 level of significance. 0.05 on a one-tailed test, on the bottom, we'll say, the critical value that you would compare your number across, would be the critical value below which 0.05, 5% of the distribution lies, right? But if you're running a two-sided test, now we're looking for the values below which lie 2%, 2.5%, and above which lies 2.5%. So when we do a two-sided test, we divide the alpha level, essentially, right? And so that could potentially, normally none of these tests will be close enough that dividing between a 1 and a 2 tail is gonna dramatically alter the analysis that you do. Most of these test statistics that you'll get on a test are 3 point something or 4 point something, where it's way off the distribution, it's forever away. But this is how you would alter how 1 versus 2 tails would alter your test. It alters where your critical values are. Right. Yeah.
And how do the only thing I'm really confused on is how you distinguish, just based on the question, whether or not you do a 1 or 2-sided or which side
Yeah.
you do.
I think that's a really valid question. I think this can be tough to distinguish most of the time, because normally it doesn't tell you run a one-sided test, You kind of have to get it from context and wording. And so in this problem, it says in part A, do you have sufficient evidence to conclude that students who work more than 20 hours a week have lower GPAs than those who don't? So if you see a word like lower or higher by itself, that's going to indicate one-sided test going whichever way, right? Lower or higher. If you see something like there's no difference between or there is a difference between, like, if it uses the word difference, then it's probably just asking, is it different from 0, right? Is the difference between the two different than 0? So you kind of have to get it from context, but normally if you see one of those things, you can be pretty sure.
And that really just affects the p-value you're looking for to know whether or not you reject or accept it. So none of the math changes, just what you're looking for changes.
Exactly.
Okay, that's easy.
Yeah.
The question had said they want to know if their GPA is higher. Would that change anything? Are we still comparing the p-value? If it's less than alpha, still we reject the null?
So if it had said higher than, then we would be looking at a one-sided test on the top, and we would switch our x1 and our x2, right?
Yes.
In order to make sure that that number was positive. Otherwise, you're just going to get a negative number again, you know, and then you're like, oh yeah, like it's not even close to being significant. So yeah, you'd switch those around. Yeah, Naomi.
Certain words that indicate two-sided?
I would just say anything that can be, anything interpreted as like different than 0. So yeah, so if it says something to the effect of like, is there evidence to show that the means of the two types of students like are different? If it just says, if it's just asking, are they different from one another, then it's going to be two-sided, because we don't care in that case if one group's is higher than the other groups, right? We just care, is there some difference between the two, right? All right, those are good questions. Any others along those lines? Okay, we're gonna look at problem 4 real quick, and then we're gonna skip down to do a regression question. We haven't really talked about regression yet. But we're first gonna do some confidence interval training, if you will. Yeah.
Are we doing a work here?
Huh?
Are they like, are we solving R right now?
Yeah.
Can I keep your help on this?
Yeah.
So why are we saying that? So the reason that we're saying that is we're assuming so we're saying that this number is equal. Oh, the P. P. And so then we're saying if this is truly P. And then you could add that. Right, but we're not looking at that. That would make, I just understand that's P. I just think it is P. Because we're saying, oh, we're saying that the P has low. It's not an accurate. And then I didn't. You're a hero.
Yes. No. All right. Part A. Confidence interval time. So how do we set up a confidence interval? What's the formula?
X bar plus or minus 1.96 times the square root of S squared over N.
Something to that effect. In this case, we're using proportions though, right?
That's what I was wondering about, 'cause I was
But I mean, it's essentially the same.
And in this scenario, you use p hat because you have nothing else.
Exactly. In this scenario, we're using p hat because we have no assumed value for p because we're not doing a hypothesis test. So now we just plug in what they've given us. So we interviewed 80 people. We asked whether they travel frequently. 28 said that they do. So 28 over 80 is our proportion of people who travel frequently. 52 say that they don't. What does this equal? 28 over 80. 0.35. Sweet. So that's our p hat. 0.35 plus or minus. We're looking for a 95% confidence interval. 1.96 is the t-stat or the test statistic associated with that level. We then do the square root of our p hat, 0.35, times 1 minus 0.35 over our total sample size, which is 80. And what do we get if we plug this in? .2455.
The other one is 0.45 or 455. Sorry.
Sweet. Here's an additional question. What's our margin of error?
The plus minus part.
Yeah, so our margin of error would be this bit. It's how far away from this we get. And so just from eyeballing it, it looks like our standard of, or our margin of error is 0.105. Sweet. All right. Yeah.
How'd you get the 1.96?
So for that, the easiest place to find it in this case would be to go to your t-table. And at the bottom of the t-table, there is a line that starts with Z star. And that will give you confidence intervals based off of the Z table at each of the levels of, of confidence listed at the top of the t-table.
Why would you use the table to the left, the z-score?
So we are using a Z-score. It's just recorded at the bottom of the t-table are the Z. So you could find it in the Z. Can I borrow this? It's not bad. So you could find it on the Z table. You could look for the point below which 2.5% of the distribution lies and the point above which 2.5% of the distribution lies. But that's kind of tedious and annoying.
But it's two-sided.
Yeah, it's two-sided. So you can go over to the t-table. They've got this nice convenient little zero, and you can go over to 95% confidence level on the zero. Yeah.
So this is talking about a two-sided 95 confidence interval. Is it like you test those one-sided?
No.
Or is that
That's like not even a thing. So,
I was just kind of
yeah.
curious. I was like, I don't even remember what a one-sided is.
Yeah. Yeah, don't worry about that. Okay, have people started on part B?
Somewhat.
If not, get started on part B.
In this, do we suppose that the 45% is the true value, or is that still an X bar?
What does it say?
So suppose that among the population, that's it. So it's not a sample anything.
It's not a sample. It's a population number, right?
Yeah, but we don't have two population numbers.
Do we need two population numbers?
But we do need two sample statistics.
We have a sample, right? A sample proportion, and now we have a population proportion.
We have one of these,
Mm-hmm.
and we have one of these. But we don't have two of these.
Do you need? When would we use this?
To figure out if there's a difference in mean.
If there's a difference in means between two different groups or two different samples, right? But we don't have two different samples here. We just have the one sample that we took, and now it's telling us, hey, the true population number is 45%.
That's for people without pets. She's serving people with pets.
But then what's the question?
The pet owners travel less frequently than people without pets.
Maybe there is something there. One second. Oh, no. No, we're chilling.
What?
Because it asks. The pet owners travel less frequently.
From a two different population.
Don't you just submit the 0.45 as your
As your mu? Like if they're the same population, I would understand. You just do this.
Yeah.
But because they're not.
Assume I'm changing the question to match the key more closely. The question, instead of asking, suppose that among the population of people without pets, 45% travel frequently, I'm just going to say, suppose that you have reason to believe that 45% of the population with pets travels frequently. Is there reason to suspect that that's incorrect? So essentially, treat 45% as your mu, and treat 0.35 as your p hat.
Oh, so you're not doing like.
We're not doing a difference in proportions here.
But does it look like we would? Like if we
It
thought that,
this
is that weird?
if you thought that, then that is not invalid.
Okay.
So, not doing a difference in proportions here.
Okay, but. Okay.
But
you get why we would.
yes,
Okay.
I definitely get why you think that.
Okay.
Sorry, Dan.
It's all good.
Andrew's the
Other TA.
Sorry, Dan. Yeah.
You're good.
For the margin of error on the last question, you just missed it. We wrote it down. It's the difference of your two.
It's the difference between like your p hat and either of them, right? Because this lies in the middle of the two.
Oh, and so, okay.
Yeah. So it's just the distance from your p hat or your mu to the edge of the interval.
Okay. So you have two margin of errors then?
You have one.
Oh, but you could find it both ways.
Because it's the same whether it's going up or down.
That would make sense.
On the test, you just have to write like reject, or do you have to write what that actually means?
I would say like reject the null hypothesis and conclude that, you know,
That it was a bad sample.
or conclude that like,
true mean is
the
not.
true mean is not 0.45.
Okay, because that's what it is. If the true mean is 0.5, you're unlikely to get this sample.
Correct. All right, let's roll through this again. Assuming that this question was worded a little bit differently, in the way that I reworded the question, it would have also been legal to do a two-sided test, but I'm just going to do what's in the answer key, which is a one-sided test. I apologize that this question is kind of confusing and weird. Okay, so we would set up our test statistic, which in this case is going to be a z-score, by doing p hat minus p over the square root of p times 1 minus p over n. So we've got 0.35 minus 0.45 over the square root of 0.45 times 0.55 over 80. And this gives us a test statistic of negative 1.8. So what do we do? Accept or reject? And by accept, I of course mean fail to reject. We reject. Why do we reject?
Because the critical value is like negative 1.6, so it's more extreme.
Yep. The critical value for this test would be negative 1.68. Negative 1.8 is smaller than negative 1.68, and so we reject the null hypothesis and conclude that the true population proportion is less than 0.45.
What did you get to negative 1.68? You just have it memorized, or?
I have it memorized, but you would look, since we're doing a one-sided test with an alpha level of 0.05, we would just look on the z-score or on the z-table for the critical value below which 5% of the distribution
I think
lies.
it's 1.645.
Hmm?
No.
Is it 1.64? Rick,
1.64.
I'm wrong, guys. Devastating. I may never recover, honestly.
Hang up the marker.
Yeah, hang up the marker. Yeah.
I'm not seeing where you found the critical value.
So if you look on your Z table and look for, just look on the table for where it says 0.05. And then once you find 0.05, look for the number associated with that. And it should lie between 1.64 and, well, negative 1.64 and positive, or negative 1.64 and negative 1.65.
So is the p-value the number you get when you plug in, when you find on the chart the z-value?
Right, so instead of this
The p-value, yeah, the p-value is the number you find when you plug your test statistic into
Right.
it.
So your p-value is when you plug negative 1.8 into the chart.
Yep.
When I plug negative 1.8 using the chart, I thought I got 1.059, which I thought was, oh, P is well rejected, Josie rejected. Okay, yeah, never mind, I just proved myself wrong.
That's tough. That's tough. Okay. Yeah, did you have a question?
On the T-table, 1.645 is associated with 90% cop center interval. Is that just because it's two-sided? Like, it's 5 on one
Yeah,
side, 5 on-
exactly, because it's two-sided. So it'll differ from a one-sided. All right, we're going to move on to, ooh. Kind of wanted to do that one too, but I don't think we have time. We're gonna move down to question 9 to do a regression question. That one is rejected. The p value is less than the alpha level, and the test statistic is more extreme.
Negative 1.8 is less than.
But if it's on the positive side, then it's less than. Worse on the
All right, real quickly before we start this, really quick regression review. So, all regression questions are going to, the hard part of the question is going to be calculating your estimated beta 1 and beta naught, right? And so, real quickly, how do we calculate these? What is beta 1 hat equal to? That's getting there.
Is it the expected value of x psi minus x bar times y minus y bar over the expected value of x psi minus x bar squared?
That is true. We can write it in a more concise way.
Covariance over variance.
Covariance over variance. Which is also equal to the big scary equation of. sigma yi minus y bar times xi minus x bar. Yeah.
When you're doing a practice problem in class, and I did the covariance and the variance, like, with the algebra shortcuts we learned from the beginning of class, and she was like, no, like, do the, like what he said.
Yeah, calculate it out by doing expected value of x, y minus minus mu x squared. Not squared, why am I squaring that? Yeah, calculate it out this way
For the covariance?
for the covariance.
Okay, that's what I was doing, and then she was like, no, we're practicing with the harder one. Anyways, but it's fine if we do it the way we're used to.
Yeah, do it that way.
Okay, thanks.
And then how do we find
That's fine.
beta not hat?
Y minus beta 1 hat times x, right? I guess those are all bars, right?
Yep, there we go. So beta naught is actually really easy to find once you have beta 1. Then you just need y bar and x bar, which you already had from having to calculate this, and then you just plug in your number for beta 1 and your gooch. This though takes kind of a while and is super annoying. So we're gonna take the next 15 minutes and we're gonna calculate this out for this problem. So go ahead and get started. I apologize in advance, but there's basically a 100% chance that there's gonna be a question like this on the exam. So may as well practice now. Yeah.
This new way, which is
Yeah, but just understanding how to determine where. I think I just am trying to put my mind around how this connects to the equation where it's, like that. So I know in the middle there's this, which is your z, right? And then out here is those are your.
I very rarely send it this way, so you need to kind of jog my memory.
I'm just so kind of lost on how you determine these problems.
So with what? With confidence intervals or with hypothesis tests? What?
Don't know when you do that kind of.
it gives you everything.
I'm not able to differentiate.
You technically don't need the variance.
Like I understand, like when I see this, I know that you're calculating.
Because you're just deciding one to be x and one to be y.
You only need the
I just
variance
don't know
of
like what to plug
size.
here.
So you pick based on the original etc. So I had price as y and square feet as x because it's right. Y equals beta naught.
And then
one
there's the
x.
difference. I just don't know which one.
They give you, yep, that totally makes sense. Okay.
Yeah. So
So basically with the confidence interval, you're trying to find the confidence interval, right? And then you stick this in the middle, and then you multiply.
So you're gonna find side of these. So you're gonna have the values associated with this. So you're gonna have positive 1.96 and negative 1.96. Cool.
But what did it start with?
So that's what we're starting with. And then you're gonna plug this whole thing in there.
I know that this is.
No, you're good. So what we're saying here is we're saying there's a 95% chance that the test of this comes out of this is between two ends out, between these two. So now as we solve out and get mu by itself, we're turning these critical values into being numbers associated with our sample. Because we're multiplying it by this deviation, we're gonna add x bar to this. If that makes sense.
So if we use signs,
Well, so
But it's gonna end up being so we would multiply this on both sides. Then we can negatively this.
So that's your, it's a lot faster.
Yeah, no, it's like a, so,
We have everything in,
what did you get for it?
We're
No,
trying to
that's
solve.
Beta 1
Well,
is
so,
still that.
well, so the test is just like is
270,000 for
the goal of the test.
Oh, you added it?
Trying to get mu by itself.
Oh, you're supposed to subtract it, aren't you?
Well, I actually am not 100% sure.
You are supposed to subtract it.
oh, you're estimating.
It's got a weird slope. Because if you interpret the slope, isn't it supposed to be the amount you
So
just
you can see like algebraically that
go up or whatever?
So it ends up being,
for this point.
I guess it's for each individual square foot, so maybe it doesn't make sense.
so 269, 856.
Yeah.
But this is the.
What's confusing me is that it says the sales price is measured in thousands of dollars.
Oh, right.
But I don't know, so this is the average sale price is 270K. Is that like 270,000 or still just 270?
Oh, that actually makes a lot of sense.
We can't get it.
Do.
Sorry.
No, no, you're good,
Not to
you're good.
interrupt.
No,
You're good.
no, you're good. Well, I just didn't know if I should tell you just what I got. And I was like, so, use that one, and then like, this part kind of confusing. Oh, sorry.
Did you just do the covariance over, so like the covariance is.
I'm gonna start writing stuff on paper, but if you've got questions afterwards, we can talk for a bit.
Yeah, but then with that, we're like, okay, so that's our.
Yeah, we don't have to calculate.
Just give us
What? Are you kidding me?
We just put that in to find the beta. Oh wait, were you wanting for us to find the variance and covariance?
Well, that's what I was hoping it was gonna make you do, but it just gave it to you?
Yeah.
What? Are you kidding me?
No, I was like, this feels too easy.
This is very easy. I will note that it probably won't be this easy.
Wait, then give us a different one.
Okay, let me try to find a different one.
I was like,
Let me see.
It's 13,500 over $150.
so it's, that's not, so is Y bar supposed to be 270 or 270,000? Because it's already measured in thousands.
Let's see.
That is weird.
Hope that's the wrong class.
I think it would.
Because it would make more sense if
It might
was
just
like,
give you a more useful slope.
if it was 270 minus 144, it makes a lot more sense than 270,000.
Yeah, very true, very true. Yeah.
Okay, that also confused me. I was
Yeah.
like, wait, because then I thought the square feet is not measured in thousands.
No.
So it's just like, I have like.
Okay,
what, 600,
I might step on
700,
Jens's toes a little bit because I think he was going to cover this on the other one, but
It's okay, I've never met this man in my life.
you've never met Jens.
No.
What? There's not an example? Yeah, there's an example on the homework, but you guys have already done that one.
That's correct.
Yeah. If like we did see one of these in the test, and for some reason we just really spooked about trying to find covariance again, if we did use the x1 minus x bar multiplied by y, sorry, I said x1, xi minus x bar multiplied by yi, like that whole thing, you know?
Yeah.
And for beta 1, theoretically, could we still use that on the test?
For sure.
Okay.
Yeah, you can use
The
the.
what? The
So-
algebra shortcuts for the variance and covariance?
Well, algebra shortcuts. Algebra shortcuts is something like this, right?
Yeah. Okay.
So this isn't super relevant to.
Yeah, I guess I was just thinking the easier ones for me.
What do you mean? What do you mean by the easier one?
Like just
Describe
not
to
the
me.
whole written out, the like, do you know what I, like not the summation of this and that, it's just like E of.
Did you like that estimate
Yeah,
value
yeah.
for X and Y?
So you're saying this instead of this.
Yes.
I mean,
Even though I know they're the same thing.
yeah, they're.
I'm just more familiar with them.
Yeah, no, for sure. You can use either one of these. They are the same. And those, yeah, that's the covariance right there. I mean, I could make something up real quick if you really wanted to practice. We could say we're gonna have x values of
3. Make one 3.
2, 4, 3,
Yes.
and 6.
Ooh.
And then we're gonna have y values of 15 point. Do I want to be mean? Yeah, I'm gonna be mean. 15.9. I was debating between having decimals or not. And then we'll have 18.
13.7.
I'm gonna make it significant. 27.2. 20.1, and then we're gonna have 28.6. All right, calculate away. Find me beta 1.
Bring me back.
Bring me beta 1. Where's, okay.
You don't even gives us nice X bars.
Also, I believe I'm going to use what was kind of the precedent on the homework, which is I believe on the homework it didn't have you adjust for sample variance. I would have to double check that. But so like if I'm finding, will that actually matter? No, that won't matter. Ignore what I'm saying.
Okay, good.
I'm rambling. What's your Y bar?
22.95. What is it? 22.95.
Is it that? Do 91.8 divided by 4.
Yes.
Huge. Who needs a calculator? Not I.
I disagree. You just use the calculator.
To verify to verify.
Verify to verify.
Who's got a beta 1 hat for me? 3.22. Is there agreement on that?
Yes.
Sweet. I obviously knew it and did it in my head, but
They're so smart.
what do we got for beta hat not? 10.1? Sweet. So now, after it makes you do this, it would probably ask some question about predict the value for when x equals 5. So then we would say like yi is equal to our intercept plus our slope times an x value of 5, and we would get some prediction for that. And then yeah.
Wouldn't it be, y hat, not y hat?
Correct. Very correct. And yeah, this would be my subscript 5. It could then ask you questions about residuals, like find the residual between predicted value of 4 and the actual value of 4. So then you could plug 4 into this equation, see what it spits out, and then find the difference between the two to find a residual.
That's the E thing,
Yeah, it's the error term. In 388, they're a bit more pedantic about that, but yeah, the residual. Yeah.
So I know for the homework, the thing that I think I got wrong is like when it asked like to interpret, like what does she want when she says like to interpret like beta not hat and beta 1 hat?
So let's say, for the sake of argument, that I don't know. What do we want our x variable to be?
Dogs.
Number of dogs is our x variable. And we'll say our y variable is a measure of happiness. Is a measure of happiness from 1 to 30. We of course see that that dogs have a strictly positive impact on your level of happiness. So if we were to interpret beta 1 hat in this case, we would say for every additional dog, you are 3.22 like random measurement units happier, right? Versus beta naught, we would say the intercept of this is if you have no dogs, this is your happiness score, right? Or you could go further and you could say this is the average level of happiness among those with no dogs. I do like dogs. I'm pro dog. I'm not like crazy about dogs, but I'm pro dog. You know, huh?
You have dogs.
I used to have a dog. He died in 2020. Big sad. I have 0 dogs, so my measure of happiness is 10.823. Okay, does that make sense on the interpretation? I have looked at the test, but I don't recall specifically what kind of the regression question is like on that. But from past tests, there are sometimes questions about what you had to do on your homework, like showing that the average of the residuals is 0. And that's pretty simple. You just add up all the residuals and you divide it by the number of residuals that there are. The other kind of tougher question that might be asked is to show that the covariance between x and the errors is 0 or close to 0. In which case you do a very similar process, obviously, to here. You still use all your x values, but then you replace the y values with your residuals, and you calculate that out. So that can be a bit of a pain, but just find the covariance and you're good. Yeah.
In this problem number 9, it gives that equation, like the regression equation,
Mm.
right there, but then you never actually like use that equation.
Awkward.
Like you use like price I equals beta naught plus
Yeah.
beta 1 square feet, but then you don't use the epsilon I.
Yeah.
Is there a reason why they gave us that? And like, if they give us that, will we ever use with the epsilon I?
So just a dash of 388 here for you. Whenever we are finding like beta 1 hats and things, these are estimators of an actual beta 1 and an actual beta naught, right? That is here in this equation. And so this equation is like what we're trying to approximate, right? And we're trying to give some approximate, estimate of this equation. This epsilon I term is the errors, which is to say, for every square foot, of house or whatever, we would predict some price level, but then there's some idiosyncratic difference between our prediction and the actual price for every house, right? That varies for a bunch of different reasons that we can't necessarily control for in our regression, right? And so we can never know what like the error term is. It's just a term that we're tossing in there to like kind of complete the equation, right? Because obviously the price of your home is not fully predicted by square footage, right? And so we need some error term that's capturing all the other factors that are affecting it, right? But we have no way of estimating that term because it's idiosyncratic for every house, and it lumps together so many different factors that it can't really be estimated. And so that epsilon I does not appear in our predicted values because we can't estimate it. It's just inherently unestimatable, if you will.
Okay, so if we see an equation like that, just ignore the epsilon.
Yeah, the epsilon is just there for like pedantic academic reasons. Like this is technically what we're trying to estimate is this formula, but you won't need to have an epsilon I in fact, you shouldn't have an epsilon I in your estimated model. All right, we are out of time and no longer have the room technically, but best of luck. You're all going to get 100%. I can feel it in my bones.
95% confident.
95% confident that you will